Welcome to The Explainer. Today we're going to tackle a concept that helps us make sense of a world just filled with endless possibilities. We're talking about things you can measure, not just count. And, well, how do you even pin down probability when the outcomes are literally infinite?
All right, let's start with something really simple, a bit of a warm-up. If you roll a standard six-sided die, how many different results can you possibly get?
Right, the answer is obviously 6. It's a countable, finite number. You can list every single one of them. 1, 2, 3, 4, 5, or 6. We call this a discrete variable. Pretty straightforward, right?
Okay, but now let's shift gears a little. Imagine you go out and buy a bag of tea that's labeled 1 kilogram. But how much does it actually weigh? Is it exactly 1 kilogram down to the last atom? Probably not.
Yeah, the weight could be 1.01 kilos, or maybe 1.012, or even 1.012458, and you could just keep adding decimal points forever. See, between any two possible weights, you can always find another one. That means the number of possibilities is, well, it's literally infinite. And this is where our simple counting method just completely falls apart.
So this huge difference between counting things, like those die rolls, and measuring things, like the weight of our tea, is really the key to this entire explainer. Let's really dig into it. Okay, so the official term for a variable like weight, or time, or temperature is a continuous random variable. The key word here is continuous. It means it can take on any value within a range, not just these neat separate steps.
And this right here, this brings us to the absolute core difference. With the die, that's a discrete variable, you can totally ask, what's the probability of rolling exactly a 3? But with our tea bag, a continuous variable, the probability of it weighing exactly 1.012458 kilograms is, well, it's so incredibly tiny that, for all practical purposes, it's 0. Just 0.
Okay, so hold on. That leads to a huge problem, right? If the probability of any single exact outcome is 0, how in the world do we calculate anything? It feels like a total paradox.
And just like our source material says, we need a totally different way of thinking about this. If we can't ask about one specific exact value, what question can we ask?
And here's the solution. It's called the probability density function, or PDF for short. We basically change the question. We stop asking, what's the chance of it weighing exactly this? And we start asking, what's the chance of it weighing between 1.01 and 1.02 kilograms? See? We start looking at ranges or intervals, not single points.
So the best way to picture this is to think of that probability distribution as a smooth curve. The probability of landing in a certain range isn't a point on the curve. It's the total area under the curve between your start and end points. We're measuring a region, not a pinprick.
Okay, so what's really cool is that a lot of these curves you see in the real world, they follow predictable patterns. So let's meet two of the absolute superstars of the statistics world, the distributions that help us model all this uncertainty. Now, there are a bunch of these patterns, but the most famous one, by far, is the normal distribution. It's the one that describes things that cluster around an average, like people's heights or the dimensions of manufactured parts. There's also the exponential distribution, which is great for modeling the time between events. But for today, we're really going to zero in on that normal distribution because it's the key to solving a real-world manufacturing problem coming right up. The real magic of the normal distribution is just how predictable its shape is. It's perfectly symmetric, and it follows this amazing little rule. About 68% of all your data will fall within one step. That's one standard deviation of the average. Get this, 95% will be within 2 steps, and pretty much everything, 99.7%, will be within 3. This isn't just a cool fact. It's a massive, massive shortcut for understanding data.
All right, theory is great, but how does this stuff actually help us make decisions in the real world?
Let's take a look at a business case straight from our source material that involves a huge manufacturing contract.
So imagine this. You've just landed a massive deal to supply piston rods to a car company. But here's the catch. The client is incredibly strict. The diameter has to be between 2.541 and 2.548 centimeters. If it's even a tiny bit outside that range, it gets rejected and you lose money. The pressure is on.
And now you have a choice to make. You've got two machines. Machine 1 is super precise. Its standard deviation is really small, but it costs an extra 3.3 lakh rupees. Machine 2 is the cheaper option, but it's not as consistent. Now you make 100 rupees for every good rod, but you lose 40 for every bad one. So, which machine is the smarter investment?
This is exactly where the normal distribution becomes our hero. We can use it to calculate the area under that curve that falls outside our acceptable range, the rejection zone. And look at this. For the precise machine 1, we're looking at about a 25% rejection rate. But for machine 2, it's almost 49%. That's nearly half of its entire production getting tossed in the scrap heap.
So let's turn those rejection rates into actual money. When you factor in the profits for good rods and the losses for bad ones, the expected profit for every single rod made on machine 1 is over 64 rupees. But for machine 2, it's less than 32 rupees. That extra precision in machine 1 literally doubles your expected profit on every single part you make.
So it all boils down to this one number. That extra profit you're making on every rod with machine 1 has to eventually pay for its higher upfront cost. And when you run the numbers, you find that the moment you produce more than about 10,070 rods, the expensive, precise machine actually becomes the more profitable choice. That is a multi-lakh rupee decision, made with confidence, all thanks to modeling uncertainty.
Okay, so let's zoom out. What's the big picture here? What's the crucial point we should really take away from all this? Why should we even care about modeling the infinite?
The big takeaway is that the real world is often continuous. It's messy. It's not made of neat little countable blocks. And by shifting our whole way of thinking, from trying to find impossible exact answers to instead calculating the probability of a range, we unlock this incredibly powerful set of tools. Tools like the normal distribution let us manage risk, make smarter financial decisions, and really just bring a sense of order to an uncertain world.
And you know, this way of thinking isn't just for factory managers. Not at all. It applies to forecasting your project deadlines, understanding risks in the stock market, or even just guessing how long your phone battery is going to last. It gives us a brand new lens to see the world through. Which leaves us with one final question for you to think about. Thanks so much for joining us.